What are we doing today? We're going to be able to use the French last name, L'Hopital's rule. L'Hopital's the guy. We'll talk about him in a second. We can use L'Hopital's rule to find the limit of expressions that result in indeterminate forms. How are we going to do this? We're going to rewrite the expression in one of our indeterminate forms and apply L'Hopital's rule until we don't need it anymore. Why are we doing this? Because there's a bunch of functions that just are too wacky to deal with on their own. And so eventually, we're going to need to figure out how to do those too. And this is how. All right. So let's talk about what actually is L'Hopital's rule. So L'Hopital's rule says if you've got a limit that would result in like 0 over 0 or infinity over infinity, or if you could like rewrite it to make it work like that, then what you can do is you can take the derivative of the numerator and the derivative of the denominator and then just try again. So we're not talking about like quotient rule. That's separate. We're saying if the limit can be expressed as 0 over 0 or infinity over infinity, then we can take the derivative of the top and bottom and just try it again until we get something that actually works. So who is L'Hopital? Well, so the guy, he was a French aristocrat who was a mathematician, sort of. I think he was more of a like with pedagogy than necessarily with like actual figuring out new mathematical theorems, or at least that's what my research sort of implied. He wasn't like top tier mathematician; he was like second tier mathematician. And so what he did is he made friends with this much better mathematician. And in fact, this entire family, the Bernoulli family, if you take like there's a bunch of uh, levels of mathematics and even like physics and stuff like that where you'll talk about Bernoulli a lot. Bernoulli comes up a ton. Um, Either him or his brother or his dad, I think, too. But Johann Bernoulli, this is the member of the family that we're talking about here. He was the actual creator of this theorem. He was the one that figured it out. He was the one that wrote it down. And basically, L'Hopital just paid him to feed him information. It was like, tell me what's going on in the mathematical world right now that I can put into my book. And he put it all into his book. And I think later on, actually, Bernoulli realized that a lot of the things that he fed to L'Hopital would have paid him far more than just 300 francs a year. And so he got really mad. And a lot of scholarly research went into proving that Johann Bernoulli was the actual writer for like 90% of what L'Hopital did. So L'Hopital is sort of the first record that we have of people commissioning fame, almost, you know. So one of the reasons why we have to wait till the end to talk about L'Hopital's rule is because we need to get a feel for how to take the derivative and all those things in every situation so that we can get an understanding of what we're about to do. So the first thing I want to talk about, and I want to harken back all the way to like the first week or two of school. At some point, I told you the limit as x goes to 0 of sine of x over x approaches 1. That's and I said I think that is sort of something we're going to take as gospel. We're not going to know why it's true. I'm just going to tell you that it's true, and we're going to use this as sort of the format, and we can do stuff with it. Well, now I can actually show you why. So L'Hopital's rule requires first that we check to see if we have an indeterminate form. if I plug in 0, like the limit as x goes to 0, we're trying to figure out what this is at 0, or at least arbitrarily close to 0. Well, if I plug in 0 here and 0 here, what do I get? I get 0 over 0, right? This is what we call indeterminate. So it's 0 over 0, so L'Hopital's rule applies. So what I can just do is I can say, all right, well, the limit of this is the same as the limit of the derivative over the derivative. So what I can do, say, okay, well, limit as x goes to 0. Let's take the derivative of the top. Derivative of sine is cosine. What's the derivative of x? Is 1. Well, now let me try and plug it in. Well, what's the cosine of 0? Is 1. This I don't need to plug in. So the limit here is 1. So this is one way of showing why the limit as x goes to 0 of sine of x over x approaches 1 by using L'Hopital's rule. Now there's a much more complicated way to do it sort of from first principles, and we don't need to do that now because we've been given this as a tool, L'Hopital's rule. All right, so let's do some more problems. So we're going to be able to use L'Hopital's rule to evaluate functions that we just would have never been able to do before. Like if I try, and again, the first step, the key is always to check. Here, do we get 0 over 0 when we actually go? Yeah. 9 minus 9 is 0. 9 squared is 81. Minus 81 is 0. So ta-da, right? So let's do this now. What is this approach? Well, we're going to use L'Hopital's rule. So what's the derivative of the top here? X minus 9. Take the derivative of x and we get 1. Take the derivative of negative 9 and we get 0. So we're good there. Now take the derivative of the bottom. The derivative of x squared is 2x. The derivative of 81 is 0, so we don't need that anymore. So we've got 1 over 2x. Well, now let's let the limit approach. Plug in 1. Still 1. Plug into 2x. 2 times 9 is 18. So my derivative is 1 over 18. My limit is 1 over 18. And that's what this approach is. If you were to graph this and see where it goes at 9, you would get 1 over 18. Now, there's other ways to do this. You don't have to do it this way. Like, back when we first started, my expectation would have been you take it's a difference of squares, so you break it up into the difference of squares. And then you can cancel. And then you can plug in 9 and you get 1 over 18. But I don't know about you, but this is much easier. L'Hopital's rule, so much easier. If you can show that it's going to be a 0 over 0 situation at that place, then use L'Hopital's rule. It makes it so much easier. Let's do another one. So take a look at this. Once again, we could have done it we can do this a different way, right? We can say, all right, well, wait a minute. This doesn't match our situation. We need to have this and this be the same thing. So let's put a 13 down here and a 13 up here, right? Well, so now sine of a over a gives us 1 as x goes to 0. So that's 13. But that's a lot to remember, right? You don't want to have to remember that specific situation, and maybe you're not cool with, having to just add stuff in. I don't want to have to do that every time necessarily. Let's use L'Hopital's rule. Well, I plug in 0, and so I get 0 over 0, right? So let's use L'Hopital's rule now. Limit as x goes to 0 of, what's the derivative of sine of 13x? That should be 13 cosine, right? 13 cosine of 13x all over x. Well, all over, sorry. Derivative of x is 1, right? Derivative top, derivative bottom. There we go. So now we plug it in. Well, what's the cosine of 0? It's 1, right? So I take it and it approaches 13 times 1 over 1, which is 13. So again, I'm not telling you that you have to do it one way or do it the other way, but I am telling you that here's another tool if you want to do L'Hopital's rule pretty much every time. As long as you can show that the original function would be either 0 over 0 or infinity over infinity, like that, then you know you're fine. Let's do another one. So take a look at this one now. So we've got the limit as x goes to infinity. Do we have infinity over infinity? I think so. Let's find out. We've got, I plug in infinity here. 3 times infinity squared minus 7 times infinity. That's infinity, right? 7 times infinity squared plus 3, still infinity. So this is an infinity over infinity situation. So that's indeterminate. We're good. So now let's use L'Hopital's rule. So we take the derivative of the top, bring down the square. This becomes 6x minus 7 over, bring down the square, 14x 14x, and then the plus 3 goes away. And again, we look at this and we say, all right, does it work yet? Well, I plug in infinity to see if it works, and I still get infinity over infinity. Still indeterminate. So guess what? I can just do it again. Let's just do it again, right? So now we can say, well, then the limit as x goes to infinity of, take the derivative again. Derivative of 6x is just 6. The derivative of negative 7 is 0, so we can ignore that. Derivative of 14, x is 14. And so we can now say, all right, well, let's plug it. Oh, there's no more x's to plug in. Cool. 6 over 14 simplifies to 3 over 7, right? And once again, if you remember, the original way I showed you how to do this was, okay, we're going to infinity anyway. This 7x term and this 3 term are meaningless. They're literally meaningless because these x squared terms, these quadratic terms, are going to grow faster. So this, the limit as x goes to infinity of this when we go to infinity land gives us the same answer as this, right? And then we can just cancel out the x squareds. And I got the same answer. Again, I'm not telling you that there's one right way to go here. There's not. There's multiple right ways to go, and you will get the same answer every single time as long as you're doing good math. But part of the reason why we have L'Hopital's rule is it's a really great way to do it, and it's a really easy one to remember. And as long as you double check before you start, and the reason I'm being such a stickler on talking about this, as long as you check before you start that it's applicable, is because we had like 2 hours just talking about L'Hopital's rule and how they grade it on the AP exam. If you don't check, if you don't say, hey, look, it's indeterminate before you start, they actually dock you a point just for not checking, hey, it's 0 over 0. Hey, it's infinity over infinity. So make sure to do that, because that will literally give you 1 point just for saying, hey, L'Hopital's rule applies. Check. 1 point. So do that. Okay, this one, what's going on here? This isn't in a fraction, right? So in order to use L'Hopital's rule, we have to have a fraction. If I tried to plug this infinity in, it's not going to give me anything except infinity minus another infinity. We can't do that. But what I want to tell you, and logs are going to be your best friend with the most complicated ones. Let me show you why. Because with the natural log here, when you subtract two natural logs, that means you can divide them on the inside. So this we can rewrite as the natural log of, right? So what we're really doing is taking the limit as x goes to infinity of the natural log of this thing. But now you're thinking to yourself, okay, well, how does this still work with the L'Hopital's rule? Well, remember I said way back when limits, you can take them and you can put them on the inside like that. So what we're really gonna do is we're gonna be like, okay, well, whatever this is, whatever 3x over x plus 3, whatever that goes to as x goes to infinity, I'm just gonna take the natural log of that. So the way that you detail your work is up to you. What I'm going to tell you is normally I'll do something like this. I'll sort of identify, hey, this is the thing I want to take the limit of, and then I'll come back at the end. So I'll be like, okay, so what I want to find, the limit as x goes to infinity of the thing on the inside of that natural log. Well, now infinity over infinity, right? 3 times infinity is infinity. Infinity plus 3 is infinity. So this is indeterminate. Check. L'Hopital's rule applies. So let's use L'Hopital's rule and take the derivative. What do we get? The derivative of 3x is 3. The derivative of x is 1. The derivative of 3 is 0. So I'm left with 3 over 1. So the limit as x goes to infinity, this approaches just the number 3, right? So now that I've done this, I found the limit of what's on the inside. So the limit as x goes to infinity of this thing is the same thing as saying that, right? So our final answer is just the natural log of 3. So what makes this one slightly more complicated is this situation right here, getting from this step to this step. This is probably the biggest, most problematic situation we're going to have to deal with. And then likewise, from there is, okay, how do I actually deal with this? Well, I take this thing on the inside and I figure that out. And then whatever my answer is, it's just going to be the log of that. Okay, so don't overthink this too much. But those two steps are probably the biggest hurdle to getting one like this correct, because it's just remembering how to deal with how that looks. All right, let's do another one. Here, same idea. How am I going to work with this? This isn't indeterminate. Well, but what we can do is we can take this one. Let me scooch this up a little bit. We can take this one. We can find a common denominator and turn it into a fraction, and then we'll see that it works. So when we go through and find our common denominator, we end up with the limit as x goes to 9 of x minus 9 minus, because I'm basically just getting a common denominator, which means that this guy's going to go up here, this guy's going to go up here, and then these are going to be multiplied on the bottom, right? And so if I plug in 9 here, if I plug in 9 minus 9 is 0, minus natural log of 9 minus 8. Well, the natural log of 1 is also 0. So we got 0 on top. Looking good. So this is 0. And then on bottom, I plug in 9 and I get 0 on bottom. So I get 0 over 0 again. Now I can use Hopital's rule. Remember, all I'm going to do is I'm going to take the derivative of the top and take the derivative of the bottom. Well, what do we got? We got derivative of x is 1. Minus 9, that goes to 0. Minus the derivative of natural log of x minus 8, which is 1 over x minus 8, over, we got to use product rule here. So we got left d right plus right d left. So 1 times the natural log of x minus 8, and then plus x minus 9 over x minus 8. So that's what we get over here. So we end up with natural log of x minus 8 plus x minus 9 over x minus 8. And if I plug everything in, I'm still going to get, I think, 0 over 0, because I'm going to get 1 minus 1 on top. And on the bottom, I'm going to get 0 plus 0 over 1, which is 0. So this is sort of really ugly looking. I don't want it to be this ugly looking. I'm going to make life a little bit easier for myself. And I'm going to, instead of trying to take the derivative of all this stuff straight away, I'm going to simplify the fraction a little bit, get it out of being such an ugly complex fraction. So what I can do is, because I've got this x minus 8 in the denominator of everything, I'm going to multiply the top and the bottom by x minus 8. And that'll cancel this out here, turn this into an x minus 8, cancel that out down there, and turn this into x minus 8 times the natural log of x minus 8. Okay, so hold on. Let's see what this is. This is, so we're going to do times on top. So we got x minus 8 minus, this cancels out, and we're left with minus 1. X minus 8 times natural log of x minus 8 plus this thing with that cancels out, we're left with x minus 9. So let's clean this up. Let's clean this up so it's not so ugly anymore. I mean, it's still pretty ugly, but it's better than it was. Limit of x goes to 9. Don't forget about that. Limit as x goes to 9 of, well, minus 8 minus 1, so this is x minus 9 on top. And we got this silliness. So now, once again, we try everything out. We get 0 over 0, which is good. So this is 0 over 0 again. So we can use L'Hopital's rule again. We take the derivative on top. We get 1. That's a good sign. We take the derivative over here. Left d right plus right d left. So we get left d right plus right d left. Plus the derivative of this thing, plus the derivative of this thing. Oh, this x minus 8 over x minus 8, that's 1, right? Hey, this is looking good. 1 plus natural log of x minus 8 plus 1. Now, let's try the limit again. Well, the only place there's to plug in is here, and this comes out to 0, but now look what we got. 1 over 1 plus 1. So we had to do L'Hopital's rule twice. We had to do a little bit of shuffling around, but I can't imagine doing this problem literally any other way. Like, if you told me, Mr. Webster, you would have to do this, but you can't use L'Hopital's rule, I'd probably cry. Because I don't think there is a way to do it. Or if there is, it's so needlessly complex that this is significantly easier. All right, 2 more. So what's happening here? We've got 2x squared times e to the negative x. And we're going x goes to infinity. So once again, I need a fraction. I can't do this without a fraction. So let me rewrite this. E to the negative x just goes into the denominator as e to the x, right? So this is the limit as x goes to infinity of 2x squared over e to the x. Now I plug in infinity. This goes to infinity over infinity. The Hopital's rule is good to go. Let's take the derivative. On top, on bottom. I plug in infinity again. I still get infinity over infinity. So that's good. So let's take it again. And of course, I should be including my limits. And I take the derivative again. Derivative of 4x is just 4. Derivative of e to the x is e to the x. And now when I go through and do it here, look what I get. I get 4 over infinity. That's no longer indeterminate, right? If I take 4 and divide it by a needlessly big number, and it's getting bigger and bigger and bigger, we know that this goes to 0. Okay? So last one, and this one probably is the most complicated. And in order to do this, we're going to have to do something kind of weird and seemingly unnecessary. But what I'm going to tell you is that this is a tried and true method. If you've got a something to the something power, if you start out with this one step, it's going to make your life a lot easier. So let's look. What I'm going to do is I'm going to rewrite this. Wait for it. We're going to rewrite this because we don't like the fact that this exponent is here, right? Because I can't do anything with that. Well, the only way to get an exponent out from somewhere is with a natural log. And I'm going to show you 2 ways that you can do this. Exact same method. There's the way that I was taught, and then there's the way that the book does it is slightly differently, and I want to show you both ways because I think maybe one might resonate with you better than the other one. So I'll do one and then I'll do the other one, and you will always have the choice of doing the one that you like best. So whenever you have like two inverse functions, they cancel out, right? If you take +2 and you take -2, those cancel out. If you square something, then square root, they cancel out. If you multiply by 2, then divide by 2, that cancels out. Same thing with logs and exponents. So if I were to do e to the natural log of something, then that's just the same thing as what's inside there. And as I said, this is something that I was taught, and so this is just a pattern that I recognize because I've had it drilled into me. Um, for probably all of you, this is the first time you've ever seen somebody do something ridiculously like that, and that's fine. Um, but so here, this is a pattern that you can use. So if you see something ugly and nothing else is working, if you do e to the natural log of whatever it is, sometimes that'll help you break things up. So let me take this factoid and move it over here. And then we're going to use it. We're going to, because we don't have any other way to, because that needs to somehow turn into a fraction. How do I even do that? So here's what I'm going to do. I'm going to do e to the natural log of this, just so I can play around with it, see if I get anything. So the limit as x goes to 0, and it has to be from the right because you can't go from the left with natural log, right? That's another hint. Yeah. Of e to the natural log of 7x to the 5x. What's really great is, well, hold on, I know how to mess around with this, right? Power rule, I can take the 5x and bring it down. So somehow not somehow, but with this method, we've gone from having this thing to something that maybe will look a little bit easier. 5x times the natural log of 7x. Maybe I can do something with that. So just like we did a couple problems ago, we're going to sort of enter into, just like how we sort of entered into the natural log and we found the limit of what was inside, and then we can come back out and we can plug it back into the natural log. We're going to do the exact same thing for this baby right here. So we're going to take this thing and we're going to try and find the limit as x goes to 0 of that. Maybe that'll be easier. So what we want is the limit as x goes to 0 from the right of 5x times the natural log of 7x. So if I were to try and plug this in, and this is something that's gonna help us a little bit, I plug in 5x, well, that's 0, right? Okay, 0 we can work with. I plug in natural log of 7x. Well, what the natural log of 0 as it goes towards 0 from the right approaches negative infinity, right? Because think about it. We're saying we're getting closer and closer to what exponent turns e into 0. And so if we get closer and closer and closer, if you think about the way that a natural log curve works, we get closer and closer to negative infinity, that exponent gets closer and closer to 0. which is what we're trying to figure out, right? So this approaches negative infinity. This approaches 0. That is indeterminate, but we still need to get it as a fraction. So what I want to do is I want to call attention to this. Remember, infinity and 0 have a very close relationship. When infinity is in the denominator, then 0 is what we get, right? Something over 0 is infinity. Something over infinity is 0. So infinity and 0 are reciprocals, basically, if you want to think about it that way. I mean, like, I'm being very glib. I'm sure there's a lot of mathematicians out there who will yell at me for saying that. But if you think about it, infinity and 0 are kind of like reciprocals. 1 over 2 versus 2 over 1, right? Infinity over 0 versus 0, 1 over 0 is kind of like infinity. 1 over infinity is kind of like 0. So they're kind of like reciprocals. So there's a lot of ways to think about it, but probably the easiest was, so this is already negative infinity, right? Can I turn this into some sort of infinity? Well, we said that this was 0, right? Well, if this is 0, wouldn't 1 over this be infinity? So what if I took this and I put it in the denominator as the reciprocal, right? Because you could do that. You can say times 2 is the same as dividing by a half, right? Times 2/3 is the same as dividing by 3 over 2. So times 5x is like dividing by 1 over 5x. So this kind of, and I say kind of, but it is the same as the natural log of 7x divided by 1 over 5x. And this is infinity over infinity. Well, negative infinity over infinity, but that's fine. That can be. So we go through, and now we're going to do this because this is infinity over infinity. This is an infinity over infinity situation. So let's take the derivative of the top. Right? Got to use chain rule, right? 1 over this times the derivative of this. We got 1 over 7x times 7. And then the derivative of 1 over 5x is 1 over 5x squared. And it was negative, so this becomes negative, right? So now let's simplify this, right? This is kind of, let's, the 7's cancel out. That's pretty clear, right? But now 1 over x and 1 over x squared. Let's try and make these complex fractions less complex. So I'm going to multiply both the top and the bottom by x squared so that there's no more complex fractions. So on top, we have x. And on bottom, we've got negative 1/5. Right? I mean, you could also multiply by the 5 too. Let's do that too, I guess. So this is 5x and this is negative 1. But it doesn't matter because the whole point is that if this is 0, this is going to approach 5 times 0 divided by negative 1, which is 0, ain't it? So did we find the limit of this? Yeah, with all this work, we sure did. This is 0. The limit as this approaches 0 is 0. So wait a minute, we found this. The limit of this thing, we found the limit on the inside, so let's bring it back. Let's bring it back to reality here. Because now we know, well, the limit as x goes to 0 of 7x to the 5x approaches e to the 0. And what's e to the 0? It's 1. Ta-da! So what I was saying is that this is the way that I was taught to do it. You go through, you take e to the natural log. The other way, pretty much the same, but like I'll show you the way that the book does it, because it's not like invalid or anything. It's just a slightly different variation on the exact same theme. So like what they'll do is they'll say, well, let y equal this. And then they're going to take the natural log of both sides instead of going e to the ln. Well, then the ln of y is the natural log of said limit, right? You know, we can still do this whole bring the 5 down thing, and then everything else is the same. The only difference here is that you're going to go through, you're going to get the natural log of y equals 0. Right? And then you have to go through and, well, y equals e to the 0, which is 1. I'm not telling you that one way is better. They're the same exact problem. It's just a matter of when I was taught this way, the merit of writing it out the way that they have it here is just, hey, it's all in one place. You don't have to think about it. And then the merit of doing it this way, which is fine. Like, I'm not telling you it's not good, but the merit of doing this instead is that there's less clutter and everything sort of stays in the equation, and then in the end you do this. I'm not telling you which way is better, which way is worse, because neither one is better, neither one is worse. It's just a matter of being a slightly different, equally mathematical way of putting it together. So, you make your choice, and you decide which way you like better. Same answer either way, right? Yeah. And again, it's sort of the same philosophy. You still end up having to do all this stuff in blue and green down here. It's just a matter of, is it built in, or is it written into the equation that you have to figure out the final answer and solve for y? Either way, you get the same